Hello. I see a few of you out there, so I'm glad to have you join me for the live stream as always. Um, it's nice to have some people check me on my audio and ask questions and those kinds of things. So um, I know it's only Tuesday, but hopefully your week started off good. We are in week 4, so we're finally starting to feel like we're getting through the time of the semester. And also, I hope that you're finding that you're starting to get more and more comfortable using the HLA language. Um, in my opinion, it's relatively trivial to do the basic things like outputs and inputs. So, in decision making and looping are all very familiar. So we're adding something new this week, which is what HLA calls procedures, which you probably know as functions from whatever language you've or languages you've used in the past. So an HLA procedure is simply what HLA calls functions. That's all it is. And there are languages out there that call them procedures, what we call functions most of the time. There are languages that call them subroutines. These are just different terms for referring to the same thing, which is an executable unit of code that can be invoked at will in various parts of a program. So we're going to add an ability to implement procedures, which you don't frequently need in this class, but a lot of people feel more comfortable if they know how to do that, and they feel like they have more control over the design of their software. So we'll get that this week. Well, you see my agenda. So we'll look at some demos from last week's lab. Uh, I, I don't do this every week, but most weeks I do run some demos just to kind of highlight people who took the extra time to do something that looked a little bit nicer than the average submission, or that they tried something a little different that worked out well. So we'll see some of those this week. The I'll grouse a little bit more about just taking the time to make the grader's life easier when it comes to your labs. The gargantuan effort of putting an extra NL symbol in a couple of places in your code, and I say that sarcastically on purpose because I don't think it's a big ask, and it makes my life a lot easier, and it makes it a lot less likely that I will make mistakes when I'm evaluating your work, which is of your concern. Making my life easier may not be of your concern, but certainly helping me reduce the amount of mistakes I make when I'm assigning grades to things will be of your concern. Okay, we're going to add some X86 instructions to the mix this week, so we will add I wish I hadn't said that, but we will add the add instruction, which is exactly what you think that it is, and we will add the sub instruction, which is subtract. And in the HLA language, we can write those as exactly as we would in X86 assembly language. So we will have 3 instructions, move, add, sub, that are exactly as we would write them in X86 assembly inside of our HLA code. And this is one of the great things about this language, in my opinion, is that it lets us do that while we hold on to high-level features like if statements and loops and functions, what they call procedures in HLA. So we're starting to add into our library of X86 assembly language instructions. Yeah, that's it. I'll try to do a whole bunch of different examples of procedures so you can see the different setups, the different usages that you might be accustomed to when you write functions in other languages. I'll try to give you a bunch of those examples. The one sort of major difference in HLA from the languages that you've likely used is that it doesn't have return values from functions in the way that you are accustomed to. So that takes a little bit of getting used to. So when you look down in my agenda and it says return values, that's on purpose, because return values are not return values as we like to think of them in other languages. But there is something similar as long as we understand what's happening. Okay, So that's the agenda for the week. I'm going to pick one of the 10 sections. Let me blow this up a little bit. Okay, that's too big. Okay, so we are in week 4. The big thing is working with procedures, but we're also introducing the add and sub X86 instructions to the mix. But the sort of easier usages of them, and then next week we'll start diving deeper into doing arithmetic on the X86 processor. So let's walk through the module, and then I'll do demos. And or should I do the demos first? Yeah, let's do the demos first. So let me bring up the goals for this week, which is mostly how do you implement procedures, functions in HLA, and then how do you invoke them in HLA. But let me switch views, and let's do the demos part first before we do that. Okay, so I believe you can see now. And I'm not going to really talk my way through this. I am just going to quickly get to where I want to be. Okay, lab3.hla. Oh, I had a whole demos folder, didn't I? Yeah, let's do it that way. Okay, so quickly through the demos, just so you can see the some of the things that your classmates did. So, and I'll just point out to you why I'm showing you these. And also I will point out to you how I go about testing this code. So I like that this person in their prompt showed that they were reading the instructions and paying attention to what's supposed to be going on. So in the prompt, it says, this is a value that's meant to go to DL, which is just kind of a cool extra little touch that they added. So you're limited to values from 0 to 255 because this is an unsigned 8-bit integer. If you're struggling with what ranges are appropriate, you can sit down and actually do the math. In fact, I'll do that here in just a second. So how do I know it's from 0 to 255? Well, Google would tell me if I asked it. There's a very good Wikipedia page on integer computer science. But I could also just do the math if I wanted to, or I could use a calculator, and I could figure out that if I set all of the bits in an 8-bit sequence to 1 and add all of those 2 to the 0, 2 to the first, 2 squared, 2 cubed, all the way up to 2 to the 7th, if I added all that together, I would get 255. That's as much data as you can fit in 8 bits. So what I did is I just chose kind of, I used the same input values for everybody. And of course they have to fit in the range. It'll be more meaningful the way I test here in just a second. So I like the way this person did the display. So they showed, they went to the trouble to actually do kind of a much fancier looking display of the values. Made a table out of it, DL, CL, BL, and AL, and I can quickly see that those values match. So now for the next set of inputs, I want to input values that wouldn't fit in 8 bits, but that would fit in 16 bits. So if you have a 16-bit value, you can go all the way up to 65,535. But I don't want to get to input the same 66, 77, 88, 99 because all those would also fit in 8 bits, and I wouldn't catch out potential mistakes that a person made if I give 8-bit values again. So I'm going to give values that will not fit in 8 bits, but will fit in 16. And the way I did that is I just went 4 digits, 6666, would never fit in 8 bits, but it will fit in 16. 7777, 8888, 9999. And then I'll have to scroll a little bit just to show you that they use the same table. So there's the 16-bit outputs. Notice the nice heading, very nice touch. And then the required 8-bit outputs, all good. So now when I was testing, I got to the 32-bit ones, and I want to put values that wouldn't fit in 16 bits to potentially catch errors, but would fit in 32. So I have to be above 65, 535. So the way I did that is I went 1, 2, 3, 4, 5. That won't fit. 1, 2, 3, 4, 5. That won't fit. 1, 2, 3, 4, 5. That wouldn't fit. 1, 2, 3, 4, 5. Those values are all too big for 16, but will fit in 32. And then I could use that to test the output. So the reason why I'm showing you this person's is because I like the way that they formatted their output. And then I'm using this to explain to you how I go about testing your code, which I hope you are also doing. But I don't think everybody is. So this doesn't take very long. It is a good exercise, though, for thinking about what good testing inputs would be. That's a good exercise to go through for yourself. And it's also a skill you need to develop. How do you test software interactively? What kinds of values can I input into a piece of software that would possibly trigger mistakes? And then I also tested the loop functionality on all of these just to be sure. And I didn't need to go through twice, so I Control-C to kill that one. So nicely formatted output on that one. What? This one. Okay, so this person discovered multiple things and tried it. So this person discovered how to clear the screen, which actually doesn't take that hard, is not hard to figure out in HLA, because you can use Google and find it probably. But that's not to take away from the fact that this person took the time to figure that out and thought, wouldn't it look nicer if I did that? And the answer is yes, it looks a hell of a lot nicer. Also, by the way, notice that there is a preamble. There's a title. There is an explanation of what's going on in the program. This person figured out how to use colors. So you can see the FUN, I hope, are different colors. How did they figure that out? They searched through the HLA standard libraries, possibly in combination with doing some Google searches to figure that out. But the HLA standard libraries actually give you a lot of control over your terminal output, and you can do stuff like this. Usually, one person a year will go this far with it. I love it when more people do it. So props to you for doing this. And then that's really all I wanted to show you. I mean, I can sort of go through one round and show you that they had nice, consistent output as well. Also, they had a pause at the end of the section, which notice what happens at the end of the section is that the screen clears, the title is repeated, the preamble is repeated, and then round 2 starts. Those are very nice output touches. Super, super, super nice. When I kill this program, by the way, you'll notice that my terminal screen changes colors. That's because the person who programmed that code restored the colors of the terminal at the end of their run. So I thought that was a nice touch. Here's another one. So the kinds of things that stand out about these programs, notice that there are blank lines in the output, which makes my life testing this code a lot easier. And I bet anything that it made the programmer's life easier when they tested their code as well. That's also kind of a sign that they probably did take the time to test it and kind of looked at the output and thought about how does it look and is it easy to read, and that's totally worth it. It's totally worth it. Makes you stand out in a crowd for sure. And notice that now there's a round 2 reminder, and then I start doing more inputs. So that one was a nicely done one and nicely formatted. Hold on, let me clear my screen as I do these so you get the full view. Okay. Here's another one that updated the prompts to which suggests that they were reading the instructions and paying attention to what's going on in their software. Like this is the input that goes in DL. And then notice the extra blank lines. That's not a huge amount of work. That's 2 extra NL characters to make all of the difference in the world in this person's output. So nicely done. It didn't take a whole lot to just show that I took the time to read the assignment, pay attention to what the code's supposed to be doing, think about how easy or not easy it is to read. Those are all just great touches. So good on them. And then I think this is the last one. No. Okay, so let's see what this one did. This one might have just been in here because it was nicely done. Yeah, so another example of just kind of straightforward, adding some blank lines, having clear prompts. A lot what many people did, which was easy to see, is they copied and pasted things and then didn't even bother to run the program and notice like, oh, instead of 1, 2, 3, 4, it says 1, 1, 1, 4 over and over and over again. Because I guess that wasn't worth the time. So this one was a good one. Has the blank lines. It has neat formatting. There's spaces between things. Kind of the obvious stuff that you'd think, how should anyone get a degree in anything if they don't take the time to do this? So this person is on their way. So here's one that I labeled as yuck. So this one I stripped out to be careful. All of the potentially identifying stuff. But I just want to show you an example of what a lot of people did. This one was just particularly terrible. It runs, okay, so please enter 4 8-bit, 4 16, and 4 32. So what does that mean exactly? Okay. I followed the instructions. As far as I can tell, it's the instructions. It's stuck because those instructions are not correct. I don't even know. I present it for your consideration. Those are the instructions. I followed them. It doesn't work. Should this person get a 0? They should, but they didn't. So now I have to rerun it because I guess that wasn't the instruction. I guess I'm just going to try them separately. Okay, so apparently I do 4 8-bit numbers and then it stops. Good job with the spacing here. Goodness gracious, right? So there's nothing identifying about this person here, but that person, if they watch the video, which they probably won't, will know who they are. But what I'm asking those of you who didn't take the time is to look at this and ask yourself if you want your name on something like this. Do you want another human being in the world to know that this is you? And to think that this is the kind of student that you are. I hope that you don't. Spacing is a mess. Well, let's keep going since this one's so awesome. Yeah, so at least it's consistently terrible. So maybe it's my fault that my instructions didn't say don't be terrible. Don't bother yourself to put blank lines or spaces between things. I don't know, but this kind of work, in my opinion, for making me spend time on this should get negative points in a just world. So anyway, I shouldn't have shown it because it gets me all upset to think about at least the loop works. So anyway, there were a lot like that. Probably nobody watching the video, so if yours was one of the spaced ones, I respect the effort, and I sincerely respect the effort that you put into making something that's presentable. It's not asking a lot of your time. Just make something presentable. that shows that you care about your own education is, I guess, how I would interpret that. So anyway, there's my demos. That one is in a file called yuck.hla, by the way, because I didn't want to put the person's name on it or in it, but someone in your class did that and submitted it to their college teacher. Okay. So that explains my next comment, because I saw enough of those where it's just kind of depressing that I'm saying this 2 weeks in a row. So this will be the last time I say it. And I'm going to take a lot less time out of my life grading these and thinking about them and being careful about the scores that they get. I'm going to give them the same attention that they got from the person who submitted it. And I think that's more than fair. Okay, so let's not talk about that anymore because it makes me sad. Let's instead talk about more interesting things. I'm leaving my virtual machine up so we can go right into looking at what these things look like in code. So I know that for most of you, you're just starting to get your handle on what an UNS8 means, what an UNS16 means, what an UNS32 means, and then we have in the mix at the same time all the registers that we're dealing with. So I'm just going to do a kind of a little thought exercise around that, which I hope maybe will help some people. And if it doesn't, well, I hope that it does, because the thought exercise helps me. So one very important thing that I think we should tackle at first before we do the actual instructions is to deal with the issue of the sizes of things have to match. So 8-bit things go with 8-bit things, 16-bit things go with 16-bit things, and 32-bit things go with 32-bit things. But unfortunately, that's not always entirely obvious what that is. And you'll see in a second what I mean by it's not entirely obvious that something is an 8-bit thing. So let me open up the editor again. I just wanted to get rid of that. No, there it is. I should have closed it first. It makes me kind of bummed out. Okay, so this is Tuesday, September 13 notes. Okay, so the things that we know are 8-bit kinds of things. UNS8 are 8-bit things. You may not know it, but in HLA, chars are 8-bit things. Eventually, we're going to see int8, and that is a signed 8-bit integer, which means it can be positive or negative or 0. These are all 8-bit things. These also are 8-bit things. Eight-bit register segments. So AL and AH, the sizes match, so you can do things between them. You can move data from one to the other, which is really saying copy the data. You can do add and subtraction between them. You can use move, add, and sub with AL and AH as a pairing because they're both 8-bit things. You can use AL and UNS8 variables that are both 8-bit things. All right, so Druid has a question. Okay, yeah, so Druid, I think you're anticipating where I'm going with this. So if I add 1 to 6 to 4 6s and then to 5 6s, yes. So Druid's question is a question of, hopefully I'll address this, Druid, but if not, let me know, because I am coming around to the idea of making sure not only that the sizes match, but things fit as well. So give me a moment, Druid, and if I don't address it, then we'll come back to your question, and I'll try to tease out some detail that give me a better chance of answering it. Okay, so the sizes of things have to match. These are all 8-bit things, which means that with this set of things, you can work with them in X86 instructions. You can do add with an int 8 and ch because they're both 8-bit things. You could do a move from DL to an uns8 variable because they're both 8-bit things. So the sizes of things have to match. We'll quickly list some 16-bit things, although in a more compressed way. In fact, let me compress these a little bit. All right, so uns8, uns16, int16 are going to be the most common 16-bit things that we use. So those sizes match, and then we have AX, BX, CX, DX are all 16-bit things. So when you are doing instructions, operations in your code, that knowing that the sizes have to matter, this grouping of things all have matching sizes. So you can do things between them. You can do moves between them. You can do adds involving them. You can do subs involving them. They all have matching sizes, so you won't trigger any errors in your code because they all have the same size. And then, of course, in our class, there will be 32-bit things as well. In 32, those would be the most common ones, and then EAX, EBX, ECX, EDX, and then a few others, but these are the ones that we most commonly use. So all the sizes match. So now here, Druid, is I think where you anticipated this section, and hopefully that's correct, but if not, just let me know in chat, and I'll come back around to that question and try to answer it better. So then where do literal values fit into this whole scheme of the sizes have to match? So what about the value 1 as an example? Or the value 256, or the value 1, 2, 3, 4, 5, or the value 777. These are just kind of, let's do a more obvious one. So what about literal values? So this is where it may not be as obvious and you have to stop and think on the thing. So these don't have sizes like these things do. Why do we know that EAX is 32 bits? Is because it is hardwired into the processor that way. You cannot make it be anything other than 32 bits. UNS32 is not hardwired into the processor, but it is hardwired into the programming language we're using. So an UNS32 and HLA is 32 bits, and there's nothing you can do about that. It's 32 bits. But when it comes to literal values, and then I think part 2, Druid, is where we'll get to your actual question on this literal values thing. What about literal values? So here, you have to ask the question, where will it fit? So with literal values, it's a matter of will it fit there, since there's no necessarily fixed size to the thing. A literal value is just a matter of what is the value and where will it fit. So for example, the value 0 will fit everywhere. It'll fit in 8, 16, or 32-bit things, which means that the literal value 0 can be used in any operation involving an 8-bit thing or a 16-bit thing or a 32-bit thing. Of course, where using a literal value makes sense, like doing an add or a subtract. So when you see a literal value, you have to stop and ask yourself, where will this fit? Because you don't know necessarily the size. 0 could be represented as 8 bits, but it could also be represented as 16 bits, and it can also be represented as 32 bits. The quantity 0. So it's not a matter of how many bits is it, it's a matter of would it fit with this 8-bit thing, or this 16-bit thing, or this 32-bit thing. The value 1, same thing. Value 1 can easily be represented in 8 bits. It can easily be represented in 16 bits, and it can easily be represented in 32 bits. So it can be used as a literal value anywhere with 8-bit things, 16-bit things, and 32-bit things. 256 is where we start to get something a little bit different. Get these lined up, otherwise it's just going to bug me. So 256 won't fit in 8 bits. And if you try to fit it in 8 bits, you'll get an error from HLA. So HLA is looking at and asking the question, will it fit here? So you can fit 256 in a 16-bit quantity, and you can fit 256 in a 32-bit quantity, but it will not fit in 8 bits, so you can't use it with 8-bit things. 99999 is a 32-bit only quantity because the biggest quantity you can get in 16 bits is 65535. So 99999 can't go anywhere but with 32-bit things. And then 65535 will fit in 16-bit. It's the maximum value of a 16-bit thing. So 65535 will fit in a 16-bit thing, so it can be represented and used in the context of 16-bit things. But there's a potential problem, and this is what Druid, I hope, was asking, is, yeah, but what if you take 65535 and want to add 1 to it? Then what happens? That's, of course, 65536, at which point it must be 32-bit. So when you have values that you are doing math on, you don't want to use more space than is needed, but you also want to make sure that you leave yourself room for growth should arithmetic happen on your value, and it should happen to get bigger than the space that it's being given. Okay, good. Thanks, Druid. So that's what I was hoping you were getting after, is what if I do math on it? So Druid in chat had a good question that anticipated this moment in our discussion, which is, what if I have values that I'm not sure if once they have math done to them, they will still fit where they started. So if there's any doubt, then you have to go bigger. Now, one thing that's true, by the way, about all computers without special help from software, your 64-bit computer can hold gigantic integer values in it because they're represented as 64 bits or can be represented in 64 bits. But even 64 bits has an upper limit. So one reality that we have to face as programmers, as computer scientists, is that numerical values have limits on computers, and we have to be aware of those limits and be prepared to deal with it when we exceed the limits. So in this class, as an example, if we get a value that's bigger than 32 bits, that's just too bad. We're going to have a problem because we can't represent that value on a 32-bit computer without some kind of clever programming and arithmetic manipulations to retain the meaning of the value. So the sort of basic guidance is you look at the potential range of values that your thing could be, and you give yourself extra room if you think that there's any possibility you could use it, you could need it. This gets more critical when we start doing multiplication, because when you multiply two values, it can very quickly outgrow the space that you have. So go bigger when you're in doubt. So let's do a couple of examples. Just like, let's just say that we're about to create some software, and we have a variable for handling user input. So I'm trying to capture this as a note. So let's say, for example, that we're setting up a piece of software and we are declaring an input variable for a menu with items from 0 to 5, 0, 1, 2, 3, 4, 5. And that menu is never going to change, and we're certain of it. What we would want is, and we're not going to do math on them, this is just an input, and the user is only going to be allowed to ever pick between 0 and 5, guaranteed. So what we would do in this case is pick the smallest thing that works. So in this case, what's the smallest thing we have in our language that would work for this input, that would give us room to store it, and is the smallest amount of space that we would need to consume to store it? An uns8, nice. So Ember and Druid got uns8, which is exactly what I would pick as well. And uns8 is as small as you can get. So if we could go smaller, maybe we'd go smaller, but uns8 is the smallest we can go, and we will never have a problem dealing with our 0 to 5 because this kind of variable is going to be limited in purpose to just that input from 0 to 5. So now let's see that we have a so let's say that we're making a piece of software and we're declaring a variable for a counter in it, and we know that the counter will start at 0, and when it reaches 1,000, we will always reset it back to 0. Let me put some spacing up here so that they're consistent. Okay, so a counter variable in a program where the counter can range in values anywhere from 0 all the way up to 1,000, and at that point we've been told our software would reset the counter back to 0. So it can never be greater than 1,000, and it can be never be less than 0. uns16, nice one, Ember. So that's an uns16, because as soon as that counter were to hit 256, it would exceed its limits. Oh, and I forgot to say to chat, we're going to do some examples where we add numbers and see what happens when we add 1 to 255. It's kind of cool what happens. So we'll see that in a second. So an uns16 here is necessary because the counter could be greater than 255. But an uns32 isn't necessary. Because we're never going to exceed 65,535. So in this case, an uns16 makes sense. So what if you're told, well, you have a variable that's never going to be negative. It can never be less than 0. But when you ask the person giving you the specification, well, what's the upper limit of the value? And they say, I don't know. Good one, Evan. And Isnam also. Yes, so uns32. In this case, if you have no clue, you're just going to have to go with the biggest thing that you have and hope for the best. So you would pick a variable that's uns32 here, even if over time you realize, well, that thing actually never got past 100, but since you were given a specification that says we don't know, then you're just going to have to give it that room as much as you've got, and then hope for the best. Okay, so I won't keep going on and on and on with that, but this kind of thought experiment is super, super useful to sort of think about, and then be watching in your programs and the software you make in this class And by the way, when you go out into the world and you work in other languages, sort of be thinking about these issues, the boundaries of different data types, what are better and worse choices for data types. So anyway, that's probably enough for that, and now we'll go look at some code. Okay, so when you have something that's identifiable in terms of its type and size, the sizes of things have to matter, right? 8-bit things have to go with 8-bit things, 16 with 16, 32 with 32. When you're talking about literal data, then you have to think about where that value can go. What is the upper boundary of that value? Am I going to be doing math on it that could change it where it moves it beyond the boundaries that I imagined? You sort of have to think about that and plan for those things when you are designing your software and picking data types so that you have the proper sizes and the capacity to handle these things. All right, let's see, there's a couple of questions in chat. So that one kid asked for 0 to 5, could we use constants or char constants, or are integers better? So, yeah, that's a good question. So you could use chars for 0 to 5, and I can't, in HLA, certainly there's no difference because the logic you're going to perform to see if it's a 0 is basically the same logic that you would perform as a character or as an integer. So I think characters and integers in the context of that menu with items 0 through 5 could both be handled well with chars or integers. Though the one thing that I would think of is if I were writing a little loop to guarantee that they gave me between 0 and 5 and nothing else. It's a lot easier to write a loop that says everything less than 6 than it is to deal with containing the range of characters that are allowed. There's still sort of a logic to it, but it's less obvious. It would be using ASCII values. So I would choose integers, but in terms of the performance of the thing, there would be no difference. It's just a little bit more obvious when you write the logic about like prohibiting values greater than 5 or less than 0 if that mattered. That's a good question though. And these are the kinds of things that this class is we hope you'll think about going through this class. When you're declaring a variable, what is the appropriate data type here? And what are the ramifications of choosing a char over an integer or a string over a char? We don't deal with strings that much in this class, but I'll just give you the spoiler on strings is that they are highly inefficient. They use a lot of memory for what they are, and if you can get away with not using a string and use a char or an integer instead, that's better. But sometimes a string is the only way to sort of represent the data you want to represent. Okay, so good question though about the 0 to 5 and chars and integers. So let me save this, and then let's go play around with some code. So we're going to do a bunch of things in this code. We're going to look at procedures. We're going to introduce the add and the sub instructions. I'm actually going to do add and sub first while we're on this idea of kind of the values moving around because we're adding and subtracting. So let's just do something super, super simple. So I'm not doing documentation because I want to save the screen real estate. That doesn't mean that you shouldn't do documentation. That means that for the purposes of my demonstration, I am trying to save space on the screen and not make you look at documentation. So, and I know you guys who are here live or watching the video later are thinking, why is he going on? I don't do any of those things. Well, it's other people. I mean, I know that, so I apologize to you. I don't know where else to reach out to you en masse like that. So anyway, apologies for the grousing. But anyway, no documentation. I'm aware of that. I'm not submitting this to anybody. I'm doing it for demonstration purposes. So let's do move, add, and sub, which is going to feel awesome because they are X86 instructions. We're writing actual assembly here, ignoring the fact that we're using HLA to help get an executable program out of it. We're otherwise going to use a lot of assembly, true assembly instructions. So I'm not going to use any variables, but I'm going to do move 1 to AL. So here's an example where I'm using a literal and I'm using a register. So when there's a literal, the question is, will that literal, can it fit in the size of the thing being referenced? So will the value 1 fit in an 8-bit register? And the answer is yes, it will, because you can represent 1 as 7 zeros and a 1. It would also fit in something bigger because 1 fits in 16 bits and 1 also fits in 32 bits. But in this case, I'm using 8 bits so that we can, so the math is easier to track. And then I'm going to sprinkle in some outputs. In fact, let's make a procedure to print it. Okay, so I decided to do both at once. And hopefully this doesn't make anybody feel overwhelmed, but I also thought, why not? We're going to talk about. Okay, good question, Ember. So Ember in chat asks, what do I mean when I say a literal? So a literal to a programmer, let me put it in my notes down here. So it's going to sound snarky, but it's not meant to be. So in HLA, one thing to just sort of immediately, I got in the middle of stuff here. All right, let me go to the bottom. All right, so we'll stop on this to make sure that everyone's clear on it. No, I never defined literal. I just assumed that people knew what that was. So I'm glad that you asked, Ember, because I'm sure there's a lot of other people who may not be entirely clear what I'm talking about when I say literal. So when we say literal in computer science, we're talking about a value. And we use the word literal in contrast to what we think of as variables in high-level programming, what we call variables in high-level programming. And in HLA, also think registers. So in HLA, a literal is a value that's not a variable or a register. And literals, I usually just say they literally are what they are. So the value 99 is a literal. It's an integer literal. It is just literally the value that it is. It's not a variable where I have to print the variable or go inspect the code to kind of figure out what the value of the variable is. It just is the value that it is. 3.14, that's a float literal. I'll just call it float for now. That's a float literal, so it's not a variable, it's not a register, it is just literally a value. We have character literals. So in HLA, it'll be a single character in single quotes, which is common to a lot of languages. C++ uses this same way of representing character literals. We have Boolean literals in HLA, true or false. It's literally the value of true that we would associate with the Boolean type. And then we can also have, we won't use them in our class, but we can have string literals as well. So those are what I mean when I say a literal or a literal value is not a variable, not a register, but literally the value that is shown to you. And then making note of the fact that the way we tend to represent literal values, numbers are easy to identify because integer literals are just whole numbers. Float literals usually have a dot in them. Character literals in many languages use single quotes. True false Boolean literals in most languages are true false. And then string literals in many languages are marked with double quotes around them. So they're not primitive data types. So a primitive data type is a keyword in a programming language. So a primitive data type in HLA look like this. Uns8 is a primitive, int8, uns16, int16, uns32, int32, char. We're going to see real 80s probably at some point, and some others. So a primitive data type is talking about a data type that is used to represent a value and only the value. So a literal is just 99 is a literal. X is a variable, right? So X is not a literal. It's some kind of variable if we're finding it in code. 9 followed by 9, the digits, that's going to be a literal. Most of the time we would assume that's going to be an integer literal. A primitive data type is not really associated with the concept of a literal. The primitive data types are data types that are used to represent data that is just data. So the integer data types are just the integers. So for most of you, a non-primitive data type would be things like strings. So in most languages, strings are not primitive data types because the string is not just the string data in an array in most languages. The string data also includes the length of the string, extra space for more storage, the maximum capacity for storage for the string data. Anything that's a struct or a class would be non-primitive data types, which means that they aren't just representing a value, but potentially many values and potentially functionality as well. Those are non-primitive data types. So I don't know if that's helping clear that up or not. So those come to mind when you're talking about literals, but they're not precisely the same concept. So we have literal values, which are just literally the value that you see on the screen. Primitive data types are data types that are used to create variables that only represent data, as opposed to non-primitive data types, which are used to represent composite things. Things that have maybe multiple fields of data in them, things that are associated with data and functions. Those we would consider to be non-primitive types. So I don't know if that clears it up. Hopefully it does help a little bit. Okay. These are good. These are great questions, though. In a class like this assembly class, that's one of the things that we hope happens is that we kind of, we pull back the covers on high-level programming. We start asking these questions like, well, what does that word mean? And what does that look like in code? And why do they do it that way in code? Some of those things will happen for us, and it's exciting when they do because that's what we like to see happen. Okay, so great question. Okay, so here we are back in our program. Let me cut out the procedure real quick. I'll just start it over. So here's the basic program, and I am moving the value 1 to AL. And what I would like to do is write a function or a procedure in HLA terms that will take AL and print the value that is in it. And then I'll show you a cool little trick. So one thing to note is that the way we're going to use procedures in this class should look very familiar to you. We invoke the procedure or function, if you want to call them that, but HLA will call them procedures. We invoke the procedure by its name and a a parameter list. And in fact, let's give ourselves a greet procedure to open up the program. So, and then you'll notice a few differences. So where do procedures go in HLA? They go between the opening of the program itself, but before the main block begins. So the procedures are all going to be in this space between the main program heading and where the program begins. So let's make a procedure greet. In HLA, if there are no parameters, then you don't put parentheses. So greet is going to have no parameters, so no parentheses at all, which is a little bit weird because when we invoke the procedure, we will include the parentheses. It's just one of those things. And then you'll notice that the way procedures are set up is the very same way that programs are set up, except for the lead in is called procedure and not program. So there's the lead in procedure, and then we have the block for the procedure, which is the begin and the end lines for the procedure, greet, greet, greet. And then in between, I tend to leave blank lines at the top and the bottom on my procedures because I find it easier to read for me. Oops, I forgot to do the include for the standard library. So these can kind of very quickly get hard to read. You just have to stop, and I find it helpful myself to kind of find the procedure by highlighting it. And now I can sort of see where it begins and where it ends and what it does. So this one is just going to say, I don't know, just playing around. A couple of blank lines. So there's my completed procedure. If you know what a function header is, you can do that in HLA, but we don't need to worry about that for a while. For now, let's just worry about how do you set up a procedure, where do you place it in the code, and how do you invoke it. Okay, so Isnam asks, so where do we put variable declarations? And so yes, Isnam, if I have variables, I would put them before all the procedures start is where I would put them. I'm not going to have any in this program, but this is where I would put them. And I'll put a note here. There. Okay, so now when I post the sample, you'll have that as a reference point. So yeah, I would do that before the procedures. They are. So Ember asked, are static variables globals? They are. This is one of the things that we get to do in this class that you probably don't get away with much, or at least you shouldn't in other computer science classes. We get to be naughty and we get to use global variables. We tried to reduce our reliance on global variables over the course of the semester, but we are going to use global variables because in the HLA language and really in assembly, that is how you would end up doing it. We can create variables that are localized to procedures, but we rarely use that functionality. Yes, so Druid is correct though. So procedure variables depends. I'll show you how to create a procedure variable. Those if you declare them correctly, they will be local to the procedure. So why are it's a good question. So like why in high level programming do we try to avoid the use of global variables so much? And it's actually a feature of high level programming languages that is meant to help you avoid making mistakes. So and so I'm kind of going backward. So when you're programming in C++, you'll start to think of the scope of variables and the limitations of scope of variables is actually something that's there to help you, the programmer, avoid making mistakes because you don't accidentally make alterations to variable values in places in the program where you didn't intend to do so. It's a great feature of high-level programming. But it turns out that the way variables are stored in the computer's memory at the assembly level, if you want a variable that lives longer than a call to a procedure, then you have to make it global so that it lives for the entire run of the program. So it's really a lifetime issue. At the assembly level, the static variables give you a lifetime that is the entire run of the program. Now, when you do a high-level language like C++, C++ hides from you the fact that it is extending the lifetimes of those variables for you at the assembly level, and giving you kind of the protections of scoped variables. Okay, but yeah, it's pretty interesting. You gain a new appreciation for your high-level languages, whereas you thought that people were writing compilers just to make life miserable. They're actually writing high-level languages and compilers to help you avoid making mistakes where possible, which is kind of, it's a great thing. Okay, but you're going to see, I'm going to do a procedure with a local variable here in a bit, just for fun. And then you'll see kind of the way we do that differently in HLA. Okay, so I did not do my print value procedure, so I'm going to do that one as well. So the one thing at this stage to be careful of is that you have the complete procedure definition before you ever have any call to it. So greet appears here, the complete definition, before it's ever called in the code, and the print value procedure is going to be before it's ever called in the code. That shouldn't be an issue this week, but if you get errors about such things, the procedure has to be, for us at least at this stage, defined before it can be referenced in an invocation. All right, so now let's do the print value one. And this one is going to have a parameter. I don't know why I don't just stretch this thing out a little bit. So here's the print value. It is going to have a parameter, and I have two choices here. It has to be 8 bits because I intend to print 8-bit registers with it. So this procedure has to have an 8-bit parameter. What did I just do? But I have some choices about the 8-bit parameter. So I could just say that the value is a raw byte, which matches the size of AL. And when it prints, it will print as hex. In fact, let's just prove it by putting 99 in here instead. And 99, I think, is 16 to the, I think it's maybe 42. So let's try it. So I'm going to move 99 into AL. It's still legal for AL. 99 will fit in an 8-bit register. And then I'm going to pass the register as a parameter to this function, which receives it as a byte. And then I'm going to print it out. And I understand that it's going to be in hex because bytes are a raw data type in HLA, which means that they will be displayed by the language in hex. So let's run that, and hopefully we see the greeting, and also we see the value 99 printed to the screen, but in hex. What am I in for? No. Oh yeah, I didn't. Oh, it's 63. So there's the value in hex, 63. And that's probably correct. But we can use a trick in HLA. So let's see, that procedure seems limited. What if I wanted to use BL? Oh, you can use BL. BL is a byte. As long as it's an 8-bit thing I'm passing in, it'll print. So BL will work. Something feels wrong though. Oh, I didn't compile it. Or did I? I saved it. Wait. Oh, I see what you're saying. Ember, you did it. You got it right. Not AL, value. Goodness gracious. There you go. Thank you, chat. You're right. That was meant to be value, not AL. Goodness. Good catch. Print the value. It's still going to print in hex, but it will be the two different registers now. Why I didn't see that, I don't know. But there you go. Good catch. Okay. So that's when we pass it as a byte. But it turns out that if we change this data type to uns8, HLA will still allow me to pass the register, but HLA will actually display this in decimal. So HLA's default display system for uns8 is decimal. So if I pass even a register, HLA is going to more or less coerce it into a decimal view of itself. So I can use this little trick. I can pass the register, but tell HLA that what it's getting should be displayed and used as an uns8, and it will give me decimal instead. Oh, I should have taken the $sign out. So that's a cool little trick in HLA that it lets you do that. You can pass the register, which is kind of raw data, but you can have HLA. You can tell it, yeah, but when you receive it in this procedure, treat it like an uns8. As long as the sizes match, it's fine. As long as the sizes match, HLA is happy to do what I'm asking here, which is receive an 8-bit thing and display it as decimal, which is what uns8 will do in this language. So we love these data types in HLA because they give us decimal outputs. All right, so there's the print. So the real reason we're doing that is because we want to see what happens with some math. So let's make this be 255. Which is fine. That's the maximum value that fits in AL. But now let's see what happens if we add 1 to it. And the way these arithmetic instructions work, I've written it in a note here. So 1 is considered the source. You can see this on my agenda, I think, still. Yeah. And then AL is considered the destination. So in these instructions, what really happens is AL will be overwritten with the result of adding 1 to AL. So this is kind of like AL plus equals 1, if you want to see it that way from high-level programming. But what happens if we add 1 to 255, which is now too big? So that won't fit. So what does HLA, what does the processor do with that? It turned it into 0. Okay, that's a good question. So Druid asks, what's the default display for char? And it is char. So if you have a char parameter, HLA will display it as the character that it looks like. So that's a cool thing as well. Yeah. Okay, so did you guys notice what happened when I added 1 to 255, it wrapped around. So let's try the same experiment. What if we add 2 to 255? What happens? It wrapped around twice. 255. Yeah, it's kind of wrapping around from this direction. So what happens when you exceed the bounds of your storage capacity is it begins to wrap around and come back from the beginning, as it were. Hopefully that makes sense. So if I add 1 to 255, then it kind of starts back at 0. If I add 2 to 255, it comes back around to 0 and then 1. If I were to add 3 to 255, it would wrap back around to 0, 1, 2, and so on. So that's still a problem because we don't have 258 now. We have 2. We do have means of detecting this situation from the processor itself that we will add into our mix in the not too distant future. Yeah, so, well, I can't. Okay, so that's a good question. What if I were to add 256 to AL? So I'm going to go ahead and try to compile this, and let's interpret the error. Okay, so why can't I add 256 to AL? Exactly, Druid. So 256 is not an 8-bit value, which means it can't be added to an 8-bit thing. So it's 1 too big. Now, if we added 255 to 255, we can add this that would fit in 8 bits to a thing that is 8 bits. And then what do we get there? Oops. So 254, but that's what you would have anticipated, right? Yeah, good one, Druid. Yeah, that's exactly what you anticipated. So this is fun to play with to see kind of what happens. Let's go in the other direction now. So let me comment these out. And we're going to leave the initial at 255. In fact, let's move it to 0. No. Here's what we'll do. Okay, so when we do that, when we add 1 to 255, it's going to wrap around to 0. Now what happens if we subtract 1 from 0? What happens? So I'll give you guys a chance in chat if you want to. So if I add 1 to 255, I get 0. So at line 29 and 0, what if I subtract 1? So Isnam is correct. It comes back around to 255. So if I subtract 1 from 0, it comes back around to the high end and comes back from 255. Just kind of wraps back around in the other direction. So in this case, I'll see 255, and then when I attempt to add 1 to it, it's going to wrap around to 0. And then from 0, when I subtract 1 from that, it's going to wrap back around to the other side to 255. So these are fun to experiment with. This is the kind of thing that you don't want happening in real software because it's a huge problem. You should have 0 donuts and suddenly you have 255 of them. What just happened? So it's really cool to experiment, but also like in the real world, you want to try to keep these things from happening. We will see that the processor has actually used its E-flags register to capture this, to know that that a wraparound happened. So what we will add in coming weeks is we will do an add or subtract, and then we'll go check and ask the processor, did a wraparound happen? And if so, I'll at least make note of that fact. So that's fun to do as well. Okay, so adding and subtracting are not big deals. All right, so we are at 255. So let's go ahead and just do another quick example. So I will move 254 into BL, and then I will sub BL from AL. And then look at AL. So what I expect to get in this case, after the subtract, I'm back to 255. And then I'm going to subtract 254 from 255, and I'm going to expect to get 1 as the last result. So that's just to show you that you can subtract an 8-bit register from another 8-bit register. You cannot subtract 16-bit registers from 8-bit registers because the size don't match. You cannot subtract literal values that wouldn't fit in 8 bits from 8-bit registers. You cannot subtract 16 or 32-bit variables from 16-bit registers either. So let's go ahead and add a static just so you can see some variable math being done. And we'll just call it X, make it an unsate. Let's add this feature. So you can initialize your static variables to non-zero values if you want. It's got a weird assignment operator HLA does. That's from the Pascal language, I think, where he got that idea. But anyway, there's my one static variable. It's an unsate on purpose because I'm going to be using it in the context of values that are being stored in 8-bit registers. So let's do that. So let's add X to AL. AL equals AL plus X. So I should get 11, I think, after this one. So AL is now 11. So let's do sub 7 from, sub 7 from X. This is just to sort of get you acclimated. So you can do these kinds of operations on variables. In this case, what I'm saying is X equals X minus 7. And it turns out that I can print the value of X in the same way because X is also 8 bits. It turns out that X was already declared to be an unsate, so that's fine. But I can print out X if I want to. So the last value should show 7. No, 3. X should be 3 at the end. Okay, so that's actually using X on the other side of the math just to show you that you can do that. Okay. I'm going to show you a couple of just quick procedure examples. How do I want to do that? Well, I'll show you one in the lab that does this. So let's look at the lab since the timing is about good for the lab. Let me get this and put it as notes. Okay, so I'll upload all of that, and I will also upload these kind of lecture notes as well. So there'll be two things in the samples from class content that I upload to the website. But let's go grab the lab. You're not going to see me switch over to my browser to get it, but I'm going to go grab the lab code, and let's just read through it real quick and see if there's anything weird going on. Let's walk through the module while we're at it. All right, so quick walk through the module until I get to the lab and then grab the code and we can switch back over and look at the lab. You're going to get a big piece of starter code with a whole bunch of procedures in it. So you don't actually have to craft procedures from scratch. You just have to complete them and then make calls to procedures in a program. Okay, so we'll have two code samples from today, just the notes about the types and sizes of things. And then also the code where I did the greet and the add and the sub and a couple of procedure examples. Both of those will appear here. Homework as always. All right, so here's the lab, and I'm going to go grab this code. Where's the raw button? What in the heck? Well, anyway. Grab that. All right, let's finish walking through, and then we'll switch the view back. I hope that I switched so you can see what I'm doing. I did. So the discussion this week is asking you to go explore processor architectures. This is just sort of a little additional, I hope, learning opportunity. Many of you already know that X86 is in fact not the only processor architecture, but what's interesting to go discover is what kind of processor is in an Apple Watch or a Nintendo Switch or the Xbox or the new M1 Mac laptops, which are just driving me batty as a computer science teacher because of their architecture, as it turns out. So that one's kind of a research and discussion kind of one, but a chance to learn some sort of bonus material off to the side. And then the first project, it's a ways out, but please do look at it sooner than later. Okay, let's switch back over and let's fire up file. I'm being kind of sloppy about organizing stuff right now. All right, so here's the lab, and let's just look through it and make sure there's not anything weird going on. Documentation. So this one does have a few static variables. Some counters and stuff. They're all uns8s. That's all we're using really for our data type right now is uns8. So we'll point out where that's not going to be a limitation, but I guess in theory you could make it be one if you wanted. Here's a greeting procedure. We've already just seen an example of that, and also it will be posted with the code samples. Here's a get number procedure. Notice that this one says it's already been completed for you. So it is here in part just to show you some additional ways to set up procedures. So this one actually has a string parameter, which is the only place we're ever going to use strings in this class is as parameters to functions, because dealing with string data at the assembly level is a huge pain in the rear, and it gets us beyond the scope of our class to spend time on it. But we can pass literal strings as parameters to procedures and make the procedures be prettier. What this procedure does is it prints out that parameter as the prompt string. But then you'll notice the way that parameters are separated in HLA with the semicolon, not a comma. And then this one takes a minimum value and a maximum value, and then it uses those as a way to limit the user's input around that minimum and maximum. Okay, so that's the get number procedure. And remember that it can be helpful to kind of highlight the entire procedure from beginning to end, since looking at the code in HLA can be kind of tough when there gets to be a lot of it. Show help. So print messages letting the player know if their guess is too high, too low, or correct. So this move here is because a comparison is about to happen. Notice, by the way, I'm not using AL, so there may be a reason for that or not. Be careful of that. I wouldn't touch it if it were me. So we're going to compare these two numbers and then print out messages, kind of like a Goldilocks. You've done this before. We just did one of these a couple of weeks ago. So if BL, which is the user's number now, is greater than the computer number, then that's too high, right? So the user guessed a number which was bigger than the number that they're supposed to be guessing. Else if BL is less than the computer number, then too low. There's only one other possibility, which is just right. So this is for a number guessing game, but this procedure is here to get you accustomed to looking at HLA procedures. I'm not uploading this code. This is solely for the live stream and the videos, but you've done this before. When you want to compare two uns8s, you need to copy one of them into a register. I used BL probably for a good reason. So I wouldn't change it, but one of them has to go in a register, just like we did 2 weeks ago. And now I can take that value, BL, which is the same as the user number value since they've been copied, and compare that with the computer number, which is what they're trying to guess. So if the number they guessed, which is now copied into BL, is bigger than the computer number, well, that's too high. If it's less than, it's too low. Otherwise, that's the right number. So that's what that procedure does, is it produces some outputs based on the user's guess as compared to the random number the computer's going to generate. Play again. So this one has a fake return in it, and I am going to do it here in the video. So you've seen this part before. But the trick here is that you can't actually return values from HLA procedures. All you can actually do is load a register with a result value and then expect that value will be retrieved later. So that's how you do a return in HLA, is you load a result into a register. In the case of this procedure, we're going to load our result into AL. So how do we get a result? Well, if they say yes, the result is true. If they say anything else, the result is false. So if, and in this case, the character is in AL, so we're just going to use that. So if the character they typed in from the get C, which will be in AL, is big Y or it is little y, then we're going to move true into AL. Which is how we return true in HLA. We don't actually return it. We populate a register with the result. So the result is true. AL has true in it. Otherwise, AL is false. So we populate AL with the result value. So this is how you affect a return, because you don't have returns in HLA. All you have is the ability to populate a register with a value, and then that value can be retrieved later. So that's the whole play again procedure completed here on the video. So now let's see how it's used. Where does that come up here? Here's, by the way, games played equals games played plus 1. Here's a random number in the range from 1 to 100, which is what this HLA routine does. And this HLA routine will give us the random number in the A register, which we're going to copy into a variable. Okay, so item number 4 says, write a move instruction to set the variable number of guesses to 0. That's just this. Move 0 to num guesses. I won't spoil everything for you, but that's all that means, right? Just overwrite num guesses with the value 0. You're resetting a counter. So here's item 5. Add 1 to num guesses. Increment it with an add instruction. Item 6. So invoke the procedure show help, which is going to look like this, with AL for the user input, that's the first parameter, and computer number as the second input. So this is what I'm recommending to you when you're working on the lab. So right now, hopefully you're asking yourself, like, why AL at this moment? So we'd have to sort of step back up in the code to figure out why AL. So if we go back to the very next thing above, we have this line of code, which is a call to this procedure get number. It's passing in this prompt string and then passing in this min and this max. And then it tells me that at the end after that executes, the number will be in AL. So the get number procedure returns the input value in AL, which means it doesn't actually return it. It populates AL with the user's input. But if I know that, then I can immediately turn around with that populated AL and use it for other things, like passing it as the user's input to this procedure. Hopefully that's not making anybody feel overwhelmed. Item 7. No. So that one kid asked, is there any sort of automatic flushing? There is not. So when you return from a procedure in HLA, there's no cleanup going to happen. The only thing that happens at the assembly level is that the flow of execution returns to the place where just after the procedure was invoked. So that's like the only kind of automatic behavior for us, other than that the parameters go away. So it is true the parameters go away, but otherwise the registers are left in the state that they're in when the procedure is done. And that is useful, but also can be a hassle that we'll see later in the semester. Yes, so the Boolean data type is an 8-bit thing in HLA. That's correct. Good question. Good to note. Actually, not a question, just an observation. So yeah, good observation. The Boolean type, true, false, those literal Booleans, those are 8-bit values in HLA. Okay, 7 is just a message with the number of guesses. 8 is invoking the play again procedure. So if we look at the play again procedure, here it is. This is a procedure that has no parameters. So invoking it means play again. And then on the invocation of the procedure, you do put the little empty parameter list. Except for I put it in the wrong place. That's after item 8. And then here we do a break if on AL. Why AL? Because play again returns AL with the true false value that we will use to break. So on number 9, we will break if AL equals false. And then 10 is one last output that says, oh, you played the game this many times. Okay, that is just a couple minutes over time. So that is video only stuff, that walk through the lab. But hopefully that's enough to arm you with what you need to solve it. There's 10 items in here. We just kind of completed a number of them in this video. So this week is when we can start to have a lot more fun in this class, because we have a lot more of the power of HLA. And we can start to make a lot more sense of what the data types mean, what the registers mean, what the sizes mean. And hopefully that's starting to slowly, or quickly would be great, but at least slowly come together for you in your head. The sizes of things, what a data type is, that's all a great experience from this class. Okay, that's it. I'll stop talking at you. So thanks very much as always for the questions in chat. Those are always very helpful and very good, and let us expand on topics that are relevant to this course. So I very much enjoy being able to do that. It makes this class rewarding to be a part of, in my opinion. So I hope you find it to be that way too. So the 2 things will go up. My earlier code sample with a couple of procedures and showing adding and subtracting and wrapping around when we exceed the range of a data size. And then also the notes where we talked about the sizes of things. So have a great week. Piazza, Canvas Inbox, office hours, as always, are available if you need any assistance with the lab, or if you're getting started on the project and need assistance. All those are available, of course, so please take advantage of them as you need. And hopefully the lab goes well for you, and you have a good week, and I will see you on Tuesday next week. Take care.